Hello everyone, welcome back to this channel. We are studying class 11 physics. In that, chapter number 6, work, energy and power. This is the part 4 of the theoretical video series. Now, today in this video, we are going to talk about elastic potential energy. We will be doing a derivation as well, right? Then we'll move on to electric power and we'll see the definition. Apart from the units and all that we all have revised previously, we will be deriving a formula P equals to F into V in the power section, right? So these two topics are for the topics of this video. So starting with elastic potential energy. In the previous video, we have discussed that potential energy is present in different forms, right? Gravitational potential, elastic potential. So this is the second type of potential energy that we will be looking for. Now, consider an elastic spring with negligible mass whose one end is tied rigidly to a wall. You can see over here, right? Over here, this is the wall, right? This slanting line indicates that this is a rigid connection over here, right? Now there are three different situations. These are not a single figure. This is three different cases, right? So let us look at the first one. We are seeing an elastic spring with negligible mass. It is tied with another block of mass m, right? And right now it is in normal equilibrium position. uh, for simplicity, what we will do, we will restrict the motion of block in the x direction only, in the x axis only, right? Now the first indicates the normal position, so we will take the normal position x as 0, right? This is the equilibrium position, right? Now, when the block is pulled and the length of the spring increases, what happens? In the spring, a restoring force will be produced. And what it will always try to do? It will always try to bring back the spring in original position. So that is why force will be acting inwards, right? And the restoring force is also produced when the spring is compressed. You can see the third figure. Here we are compressing the spring, so spring will try to move the block on the right hand side so that it comes in the equilibrium position, right? So this is the simplest example of what we are doing right now, the practical that we are doing in deriving the elastic potential energy. Now let us go for the derivation of elastic potential energy. Okay, now the same figure will be there. Now just step by step we will see the derivation. Restoring force produced in the spring while we are expanding or contracting is proportional to the change in length of the spring, but always in the opposite direction of the applied force. You see, when we are pulling the block on the outer side, restoring force produces in the opposite side, inner side, right? So we can write that F is proportional to negative of the displacement, that is negative of x. Okay, so what if we remove the proportionality symbol? We have to put a constant, so we will write F equals to minus kx. What is k? K is the constant of proportionality, right? Spring constant we will say. So now what is the work done by the applied force in changing the length? Either it is elongated or compressed. What will be the work done? The work done will be W equals to integration of kx dx, right? What is kx? Kx is the force. What is dx? Dx is the displacement, right? So force into displacement is nothing but the work, but from 0, that is the equilibrium position, to x on both the sides, right? Maximum limit of stretch is x, so from 0 to x it will be the limit, right? So k is constant, so we have removed k and took it outside. So only x dx will be there and the limit will be 0 to x. Now what will be the integration of x dx? According to the rule, it will be x square upon 2, right? But we also have to write the limits as well after the square bracket. So x will be the upper limit, 0 will be the lower limit. Okay. Now one by one we will put the limits, upper limit minus lower limit. The lower limit is 0, so we don't have to put, the whole term will become 0. So ultimately it will be k into x square by 2 minus 0 square by 2. So finally 0 square by 2 is removed, and we finally have our equation work done equals to half kx square. Now important thing is, this work done on the spring is stored in the form of potential energy of the spring, right? Because we are stretching or compressing, there is another force developed, and that is a kind of potential energy. Okay, and that only brings back the spring or the block in the equilibrium position, right? And this potential energy is called elastic potential energy of spring. Now, taking potential energy in the normal position of the spring as 0, the potential energy in the condition when the change in length is equal to x on either side is u equals to half kx square. Right? We are denoting potential energy as u, so work done will be converted into u. So u equals to half kx square. This is the formula of elastic potential energy. Right? Okay. Now moving on to the next topic, that is power. So far as we have not considered the time taken in doing the work, we have seen the concept of work, but time was not taken as a factor. Now suppose in raising a body to a definite height from a given position, time taken is 1 hour, either 1 minute or 1 second or different. The work done in each case will be same, but what will be the difference? Think about it. If we raise the object to a height, right, the height will be same, but if you are taking different timings, there must be something different. Rate at which you are doing the work is different, right? So that is why the rate of doing work is very important when it comes to do total work done. Hence we need a new physical quantity, and that physical quantity is power. What is power? Power is the rate of doing work or work done per unit time. Suppose if delta W is the work done in time interval delta T, what is the average power? Average power is delta W by delta T. Now to remove the average and to come to the instantaneous part, what will be the instantaneous power? We have to take the limit, right? Limit delta T tends to 0. Delta W upon delta T will convert into dW by dt. Now, if dW is F into dr, that means force into displacement, then we can replace dW as F into dr in the numerator, right? We have seen that dW is replaced by F into dr, force into displacement. Now, below we have already had dt, so dr by dt, displacement upon time, what will be the replacement of dr by dt? Think about it. Yes, it is v. Displacement per unit time is nothing but velocity. So finally we have concluded that P equals to F into V. Right? This is not a small dash. It may be a mistake, but you put dot in between. So P equals to F dot V. Now let us see some important characteristics or properties of power. Power is a scalar quantity just like work and energy. Its dimensional formula is m1 L2 T raised to minus 3. This you can also derive and understand how it comes to m1 L2 and T minus 3. The unit is joule per second, joule second inverse, and this unit is also called watt in the honor of inventor of steam engine, very famous physicist James Watt. Now we also have bigger units, 1 kilowatt 1000 watt, 1 megawatt 10 raised to 6 watt. Also we have some primitive unit of power. In ancient times they used horsepower instead of watt, right? So 1 horsepower was equal to 746 watt. Right now we are not using horsepower much, but to measure large power of vehicles and water pump in practice we are using this bigger unit of horsepower. Okay, now commercial unit of power, work can be expressed as product of power and time as well. This fact will give rise to another unit that is called 1 kilowatt hour. It is also called as commercial unit. So what is 1 kilowatt hour? 1000 watt into 1 hour. Okay, and in our homes whenever we are getting our electricity bill, the same kilowatt hour is expressed in units, right? So 1 kilowatt hour is 1000 watt into 1 hour, and if you convert watt into joule per second and hour into 3600 second, second will be cancelled, and finally we can write it as 3.6 into 10 raised to 6 joule. Clear? Remember that unit or kilowatt hour is the unit of energy, not the unit of power. Based on this energy, we are having our electricity bill. Okay, so that's all for this video. We have finished two topics in this video, that was elastic potential energy and power, right? And we derived a formula of P equals to FV in this section as well. Thank you.